profile from there. Yes, great. All right, so we are on. We said before that on the last class we took a look at searching algorithms. Okay, we did two types of searches. Anybody could remember the names of the two types of searches that we did? Anybody? We did searching last.
On a linear search.
Right, and we had the binary search and the linear search. Anybody want to describe what the linear search involves for us? Linear search, just to recap. Is the simpler of the two searches.
So it goes by position and checks to see if the value you want, if the value entered is in the array.
Correct. Right. So the linear search, we agreed that it goes through every position in the array from the start to the end, comparing it against the search key that we are looking for. And the binary search, we used a phrase to kind of describe the binary search, how it approaches searching. Should I call a name? Let me hear Ryan. Ryan.
So searching binary.
Yes, yeah, I want to know what is binary search. Ryan, did you? Oh, you sound like you now reach back by your computer microphone to answer the question.
Now I was getting some water.
Oh, okay.
Cool.
Very nice. All right. Yeah, what is the approach that the binary search takes to finding a value in a list of values? I'm looking for two things in particular that must be there for the binary search to work properly. Well, one thing is for it to work properly, and the second is its approach.
So you're still asking, Ryan?
So I don't
Sorry,
really
what's
remember. I remember the linear, but I don't remember the binary.
okay? Chanel, what did you say?
So I was asking if you're still talking to Ryan, if it's asking everybody. So I'm not sure, but I remember something about comparing it to the middle value or middle index. So whatever you place in your search.
Okay. All right, I'll go with that. Okay, so we said, let me just jump back to the linear. The linear checks every value, right, against the key. The binary has two things that we must know. First thing that we must know is that the list must be sorted, right, or ordered. So we cannot perform a binary search on a non-ordered list. And the second thing that I was hoping that you guys remembered was that it takes a divide and conquer approach, right? Halving the list on every search. So, right, it does this. It halves the list on every search until, of course, until the key is found or the list is no longer has elements to search. So nobody went back and watch my video or nothing. So to just recap before class, eh? All right. I say to myself, a little going on at the end of the term, Josiah.
Sir, I didn't watch your video yet, but I wasn't here for class now. But I watched you recording yet.
Okay, no problem. All right, but watch the coordinate. I don't leave all these videos there to binge watch at the end of the year. That is boring watching. Okay, you don't want to listen to me for 4 hours straight or 3 hours straight or nothing. So, all right. I mean, unless you find that very entertaining, but it's much easier to just go through and within the videos it have the little key points areas, etc., especially right after class. You all could just rewatch those just to reinforce the topics that the main points that we know. Okay, you don't have to watch over like the whole class or something. So all right, so the next thing, that was just a recap, right? This was a searching recap because we did searching last day. And now we want to do sorting algorithms. Sorting algorithms. And we have 2 sorting algorithms that we look at. Okay, 2 sorting algorithms, and they're pretty inefficient sorting algorithms, but they're very basic sorting algorithms. The 2 sorting algorithms that we're going to look at, the first one is called the bubble sort, and the second one is called the selection sort. So these are the 2 sorting algorithms that we hope to look at today in terms of developing. Okay? How do they work? We want to first talk about the bubble sort. We'll start off with the bubble sort. All right, bubble sort. And, well, a sorting algorithm, the objective of a sorting algorithm is to sort an array or a list of values in either ascending or descending order. Okay, so when we say sort, that's what we after. The objective of the sorting algorithm is to end up with a sorted array. All right, so the bubble sort, let's just take a look at how it works conceptually. Okay, so bubble sort, let's say we have an array. Right, 10 values in the array, and this array full of numerical values in no particular order. 9, 7, 2, 21, 34, 9, 90, 81, 3, 5, 80. Okay, so we have our array with values. And we want to take a bubble sort approach to this array. If we want to think about, well, how do we get this array in such a way that it's now ordered, the bubble sort approach basically starts at the left side, and it always compares with the value to the immediate right of your array, of your position in the array. And if the value on the right of the array is smaller than the current value that you're at, then you swap them. And then you do this for the next value, the next element going up to the end of the array. Let me explain. We start off with the value of 9. We look at 9 and 7. Is 9 smaller than 7 or larger than 7? 9 is larger than 7. So what we do is that we swap these values. So we'll end up with 9 sorry, you'll end up with 7, 9, 2, 21, 34, 90, 81, 3, 5, and then 80. And what happens is now we are here. This is the value that we have to compare to the value on the right-hand side. Is 9 larger than 2? Yes, it is. So we end up swapping. So we end up with 7, 2, 9, 21, 34, 90, 81, 3, 5, and 80. Okay? I'm going to take off the last 3 values so that we can finish this array a little faster. Or the last 4 values. Sorry. Actually, no. I want to just take off the last 3. So now, where are we? This is the position that we're currently at. Again, we go 7, 2, 9, and 21. Which value is larger? 21 is larger. So we keep 9 where it is. We keep 21 where it is. 34, 90, and 81. 21 now becomes the value that we have to compare to the value to the right. 7, 2, 9, 21 compared to 34 is 21, 34, 90, 81. Right? We end up here. It just so happened that this is it was a partially sorted array. So we might end up on one pass to sort out the whole array. 34 and 90. Again, 34 doesn't have to swap with 90. So 7, 2, 9, 21. 34 stays in its position, 90 is there, and 81, and now we look at here. And then we have 7, 2, 9, 21, 34, 90, 81. 90 is bigger than 81, so we end up with 7, 2, 9, 21, 34, 81, and 90. We don't have any other value to swap. So this is the first pass. This is the result of the first pass. Okay, first pass. And it just so happens that our values were ordered just enough that it looks like it's almost sorted. But on the second pass, it will fully be sorted, but it could take up to the amount of elements minus 1 passes to actually sort the entire array. Okay? So again, if we passing through it, we have a good opportunity to get this fully sorted. We will end up with, we're looking at 7 to start off with. So we'll swap 2, 7, 9, 21, 34, 81, 90. Right? And then we will have to compare 7 and 9. And of course, we could see by this point that it's all worked out, but our algorithm might still compare this. So that at the dot, 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 at the end of the second pass, we'll end up with 2, 7, 9, 21, 34, 81, and 90. Okay? So it just so happened that very early on, we ended up with a sorted array. Let me give one more example. Let's say, for instance, we have an array with values sorted almost in descending order, right? Let's say we have 9, 2, 7, 3. Okay? If we take a bubble sort approach, again, we're still using the bubble sort approach. The bubble sort approach will compare 9 and 2, and we want it sorted in ascending order. 9 and 2 is going to swap. So we put 2 here, 9 here, 7 here, and 3 here. So this is what we're comparing against. We started off here. Okay, then we have to compare 9 and 7. We end up with 2, 7, 9, 3. So this is where we end up with here. Then we end up with 2, 7, 3, 9. So this is the end of the first pass. Okay, next pass, we'll have 2 and 7. Nothing has to swap, so we'll end up with 2, 7, 2, 7, 3, and 9, just as it was. okay, because you were on the 2 here. Now we have the 7 and 3, end up with 2, 7, 2, 3, 7, and 9. Then you'll end up on the 7, you'll end up with the 2, the 3, the 7, and the 9. And this is the answer after the second pass. Okay? And again, it just so happens that at the end of the second pass, we end up with a sorted array. But you notice why they call this the bubble sort? Anybody want to guess why they call it the bubble sort?
Sir, I have no clue. That's the first thing I was wondering when they said the name. That makes no. I thought it was to do with something with grouping, but I was wrong.
The answer is that the largest values, like bubbles, rise to the top. Right? So the largest values rise to the top or rise to the front. Okay? Or end if you look at it the other way. But look at the values of the 9. The 9 bubbled its way up, and then the 7 as the next biggest value bubbled its way up. And then, of course, the 3, if let's say the 3 and the 2 are swapped, would have bubbled its way up into being sorted. Yeah? And I mean, I see your comments. The hazard, yes, what you have here is in the trace of bubble sorts, this method is pretty inefficient. You could use a flag, as you said, to see if the loop is stopped beforehand. But even with that flag, when you have very large lists, this method is pretty inefficient because it has to go through every value within the array. So if it is that you have an array of size 1,000, 2,000, and you're bubbling up values from position 0 to position 1,999, it's Chelsea have problems with the name.
So if
yeah.
it's inefficient, why we have to learn it if it's inefficient?
It is one of the many sorts that exist out there, and it has its uses. So say for instance you have a small data set that you have to manage. In the instance, using the bubble sort is not going to be here or there, right? The thing is, the bubble sort and the selection sort are two of the simplest sorts that exist out there. There are many more sorts that exist out there. Like Radix sort and bucket sort and shell sort, but those are a little more complex. These, however, the bubble and the selection, they provide a very good base for understanding the concept of sorting as an algorithm. So it's really and truly from an education perspective that they're teaching you, okay, when we start to think about sorting, we want to think about the how it is. I don't care about efficiency. I just want to get the sorting job done. And from there, then you could refine. I don't know if any of you all looked at that book that I recommended some time ago, Algorithms for Living. There's a chapter on sorting and, talking about the different sorting algorithms and, the concepts behind them and how they could be applied, etc. And, it's a good place to read up on it and, see, well, where one might be applied over the other, etc. Okay, it's just good. It's good for algorithmic thinking. All right. Don't get caught up thinking about other sorts, because these are the sorts that we have to know. All right. So how are we going to implement this bubble sort? How are we going to implement this bubble sort? I'm going to walk you through the code for the bubble sort. Okay, so let me just switch to my compiler. Let's give it a second. It's opening. Okay. So you all see my screen. Yes?
Yes, sir.
Okay. So as we say, the bubble sort works by repeatedly swapping adjacent elements. Okay? It repeatedly swaps adjacent elements. So let's take a look at how we're going to do this. I'm just going to have to head up my include stdio.h. I'll see in the font properly, right?
Yes, sir.
All right, so I think that we have everything we need here. Let me just name this bubble.c. So we have the bubble sort.c, and we have to be able to, of course, have an array. Okay, so let me open up my previous. We had linear.c. Which one? Simple binary.c, or was it linear.c? I created a random array value form, right? It was this one here. So I'm going to borrow this piece of code and put it inside of here so that we can you know, we like random arrays. All right. Time underscore t. So everybody understand where I'm at, right? And I need my SRAT. You all want to be able to set the size of the array or no? It depends on what we want to do. Do I want to be able to set the size of the array? Yeah, let's set the size of the array. All right, so we can have an array up to size 1,000. So int r, right, 1,000. And maybe we could see it in action now with a bigger array as opposed to a smaller array. And we want to say printf what? Please enter the size of your array. Please enter the size of the array you want to use. So cool. How big is this array? It doesn't matter. It depends on the size that the user says, up to, of course, size 1,000. All right, let's just hope that the user doesn't have big dreams. Scanf %d, and we go ampersand I. All right, so for I is equal to 0, I up to size. Oh, I used I already. Let's use J. Right? I is less than V. Okay, so for every position up to the size of the array, what do we want to do? Store a value within the store a value in the array for a random value. Okay, so random mod, let's say random numbers up to 500 plus 1. Okay, so random numbers between 1 and 500. Okay, between 1 and 500. And we want to print out the value stored. Let's just see it work to just make sure that everything works. We have an unexpected expression percent. Oh, sorry, I meant to put an ampersand there. Okay. So enter the size of the array you want to use. Let me see if I can get this a little larger. You all see in the terminal screen, right?
Yes, sir. Yes, sir.
Okay. Okay, good. So enter the size of the array you want to use. Let's put an array of size 50. It is not printing out. Array at size I is equal to random mod 500 plus 1. Oh, sorry, this is G, not I. Okay, so we have 50 random values between 1 and 500. But we want to sort these, and we want to sort these using a bubble sort. So we did the kind of hard work. The hard work in this is actually making that array, right? We make the array, we print out the array. We're going to do the easy stuff now. Okay, so how do we do our bubble sort? Our bubble sort is actually 2 for loops. Okay, and we have 1 for loop inside of the other for loop. And because we have to run, again, if you look at this, in terms of what we did here, we have a certain amount of passes, right? We have, for the number of elements inside of the array, we have to make those amount of passes. But then we have to check each value starting from the first value during each pass with the value right next to it up to the second to last value. So what we'll have is we have two variables. We can have H, I, J, let's say K and L. Okay, so we have K and L, and we'll say for K is equal to 0. K is, what is the size of the array? The size of the array is J, right? The size of the array is J. So we're going up to J minus 1. K is less than J minus 1. And then we go K plus plus. So this here is the amount of, this is the amount of passes through the array. Okay, and then we want to go through for L is equal to 0 semicolon. L is less than, that's a O, semicolon. L is less than I minus 1. And we'll take a look at how to make this a little more efficient in a little bit. But let's go with this. And we go L plus plus. What is this? This carries us through for every pass. This carries us through the entire array to compare values. Okay? So for every pass that we make through, we have to go through the entire array to compare values. And once we go through, what is it that we want to do? We want to say if it is that the position that we currently in, which is L, so if array at position L, the array position that we currently in, is bigger than array at position L plus 1, if it's bigger than the position to the right of it, what do I want to do? I want to swap those positions. How do I swap? Well, I have to have a temp variable to hold a value to swap. To swap a value inside of an array, inside of an array, using an array, let's say that we had 3 and we had 2 here. And we know that we want to swap these values. This 3 here is array at position L. This 2 here is array at position L plus 1. How am I swapping these 2 values? Anybody want to talk me through a swap?
So in
Iran.
what?
Chelsea. Okay. No, Chelsea. And you know, I've gone call you Chelsea and I say now Chelsea are in the conversation just now. So I'm not gonna call Chelsea name. But Chelsea, go ahead.
Okay, I'm probably wrong, but at temporary to hold one of them when it's
right. So we have you're correct. We have a temp. And what do we do?
You put array at position 0 into temp.
Right. Okay, so this is the first thing that we do. We put right.
And
so
then
we have the value at 3 in temp.
And then you put array at position 1 into array at position 0.
Right. So this is the second step.
And
so
then
you start.
And then temp into array at position 1.
Thank you, Chelsea. Okay, so you were not probably not right. You were right. Okay, so this is what we do, and this is how we swap the values. So we are about to swap the values now. All right, so we have temp, and we said that the first thing that we did was that we took the value of we took what was in position array at position L, and we put it inside a temp. And then we take what was in array at position L plus 1 and put that in array at position L. So we say array at position L is equal to array at position L plus 1. And we say we take what's in temp and we put it in array at position L plus 1. Okay, is equal to temp, and that's our swap. So we do this. We say if the value to the right or the next element value is larger. Okay, so if the next element value is larger, then you swap the values. And you do this until, of course, everything is done. And then at the end of it, we can I'm going to do it once, just showing the original array and then showing the swapped array values. Okay? So I'm going to put some printfs here so that we could put these swapped array values down here, and it's just essentially to copy this again. Let's remove that random statement. We just want to print out all the values from the array. Okay. And now if we run it, if we have an array of size 5, we had 5 random values being placed in the array, and at the end of it, we have those values in ascending order. You all are with me?
Yes, sir.
Yes, sir.
Right. Okay, good. So let's see if we could do it for a bigger array, right? Let's see if we could do it for an array of size 200. Okay, and look at that. It took these values here and it arranged them for an array of size 200. And you see, it was pretty quick still with 200. Okay, but how about we see it in action? Okay, let's try and see if we could see it in action. So we can take this here and we can put it, if you want to see it after every swap, or after every check to see if you have to swap. You will see it. You'll see it here, and then I'll put a line down here. That says, let me just see. Right. Printf. And what you call it? What did I call it just now? The pass. I forgot the word pass. Right? And pass and sign D. And what do we do here? We put what are we in? Key plus 1. Okay. So we'll get ender pass 1, ender pass 2. If you want to slow it down, you could put get char to see what happens at the end of every pass. Okay, so let's see if we can get it to work. Let's use a small value. Let's just have 8. Okay. I know why that didn't pause, and that's because we didn't have a get char after our scanf. All right, so 8. This is all of the values. This is the value 360 bubbling up towards the end here. You all see where 360 bubbles up to the end here. Look at it. It came here, right? So 360, started off in the top spot, and it moved. So 360 bubbled up. The next value that should end up here should be 261, but that will only bubble up late. So 284, right? So 284 actually will bubble up. You'll see it bubble up to at the end of pass 2. So we'll see it 284. 284 ended up bubbling up. So 130 and 284 swapped, and 284 bubbled up until it reached where it had to go. And then we could see the same for pass 3, 261. Okay, I think 189 is in position, so 189 is safe, right? And for the most part, this is it's already been sorted. So it's sorted quite early, but because of the way that we wrote our code, we still ended up doing more than we had to do. Something that we could do to make it not check values that we already put into place is to put in this line here. Remember I said that we could make it a little more efficient. In this line here, we could put I minus k minus 1, because k indicates how many places you've already put in a proper place, and you'll see less and less iterations as it goes along with this k inside of here. Okay, so again, let's use 8. 8 worked out well. So we saw the values bubble up, right? 451 ended up bubbling up. It was in the middle, and it got pushed up into place. Next, notice pass 2 has less iterations. Pass 3 has less iterations. Pass 4 has less iterations. Pass 5 has less. Because we know that by pass 6, all of these are in the place that it's supposed to be in. So it's only really checking among these values that haven't been put into place, right? And again, pass 7 will put the last one into, all right. Pass 7 has put it into the place where it needs to be. Hazard?
Yes, sir. You can explain that part either again with the minus k.
With the k? Right. Yeah. So on the first iteration, when k goes up to 1, we put the first value in the last place. Right? So let's even go a smaller array, 5. So at the end of the pass one, we know that 500 is in the proper place. So really and truly, we don't have to swing through 5 anymore. When we compare, we could just swing through 4. So because k, the value of k is 1 now after the first iteration, we could say when we are going through every value to compare it with the next, go through 1 less. Because it does not make sense comparing whatever will end up here with 500. Because we have already put 500 in place. So at the end of pass 1, we know that 500 is in place. So we know that, it didn't make sense to compare 331 when it gets in place against 500. Now, when the next one, we know that it doesn't make sense to compare 150 against 331 or 500. So that's why we say, all right, if it is that we had to compare 4 values against the one after it, now after this one, it only makes sense to compare 3 values with the one after it. The next round, it only makes sense to compare 2 values with the one after it, because after this round, the 150, after the next round, the 318 would have been put into place, and we don't need to compare anything with 320, get put into place. We don't need to compare whatever is going to be in here against 320 going forward. Because this has been locked into place, this has been locked into place, and this has been locked into place. You follow me, Hazard?
Yes, sir, I got it on the execution time faster too, sir.
Right, we cut down on execution time.
Yeah.
Okay, still not the best. Still not the best. It's still not the best algorithm, eh? But something as simple as that allowed us to save a whole lot of cycles that were wasted. Everybody's good with this? Everybody understand the bubble sort? You feel like you understand the bubble sort?
Yes, sir.
Are you comfortable with it? Good. So I'm going to give us a little break now. We can take 10 minutes. We'll come back at 2:15. And I see I see I will see you all in 10 minutes from now. We're gonna pause the recording until after break.